in section 4.2, we're going to learn about logarithmic functions. Like I said, there are two types of functions that we're going to learn about in chapter 4. The first one is exponential. The second one are logarithmic functions. And logarithmic functions are the inverse of the exponential functions. So we are going to need all of our exponent rules mastered. So this first page is a quick review of things we've already talked about. So any number with 0 exponent is equal to 1. So if you're looking at 3 to the 0, that's equal to 1. 5 to the 0, that is equal to 1. And while we won't deal with variables too much as the base in this chapter, x to the 0 is also equal to 1. And then e to the 0. Well, we didn't talk about e much last class, but e is known as Euler's number, is approximately 2.7. More on that a little bit later, but when you raise it to the 0 power, it indeed is equal to 1. So that's a quick reminder of how a 0 exponent works. The other one that we talked about last class is where with negative exponents allow us to essentially rewrite something as a fraction. So if we look at a right here, we have 7 to the negative 2. And then if we want to get rid of the negative, we can. We just have to remember that this is the same thing as 1 over 7 squared. So again, that negative exponent could be made positive as long as you take whatever its base is, in this case 7, and move it to the denominator. So this, of course, is going to be 1 over 49. Similar idea with part B. You can rewrite this as 1 over 3 cubed because of that negative exponent. And one common mistake I will see is not remembering that cubing means that you're going to multiply something by itself 3 times. So 3 cubed is not 9. What is it? 27. So it's going to be 1 over 27. The common mistake I'll see with this is someone maybe write 9, just thinking standard multiplication. All right. So one other skill that we're going to want to be comfortable with is the going the other direction. So we're going to want to start with something like 1 over 36 and write it more simply as just a number to some power. So as you go through this lesson, think about, okay, is 36 a perfect square or a perfect cube? Yeah. What is it? 6. So I can rewrite this as, well, 1 over 6 squared, or if I don't want the fraction, just 6 to the minus 2. So that ability to go backwards is also going to be important to go ahead and work with logarithms. In a similar thought process, okay, I see 8. Is 8 a perfect power of some number? Yes. Yeah, what is it? 2 cubed. 2 cubed, exactly. So we can just do 2, then to the minus, and then 3. So just being comfortable with your basic powers will be good. And I'll maybe make a little chart down below just to kind of get us oriented. Any questions on that second part? Okay. Then we mentioned this briefly last class, but where any number as with a fraction as an exponent is a root of some sort. So if you have a fractional exponent, you can rewrite it as a root. So to figure out which part of the fraction it goes where is really what these 4 exercises are for. So if you look at A, we have a fractional exponent, and then the 2 is in the denominator of the fractional exponent. So the 16, the base stays where stays kind of the big number, and then you're going to rewrite this as the square root of 2. Wherever the denominator of the fraction becomes the index of the root. Again, that is sometimes referred to as the index. Now, what about the 1? There are some options for the 1. The 1 could either be interpreted to be inside on the 16, or, I'll rewrite this like so, you could go ahead and have the square root of 16, and that 1 could be after the square root is done. Either of those are fine. I tend to do the bottom one because I prefer to take a square root, make things smaller before I raise it to some power, although we're not needing to do anything with one. And one last comment about this one. The square root is kind of our standard or most commonly used root. So whenever there is a square root, you don't need to write the 2. So the square root of 16 is ultimately just 4. I was being fairly pedantic there, but it's just a good example to illustrate where you could put the exponents when you rewrite it as a root. So for part B, we're going to look at 64, and then notice it is going to be to the 1/3, so I'll look at the cubed root. Anyone know what number times itself 3 times gives you 64? 4. So notice here, 4, because 4 times 4 is 16, and then if you multiply it by another 4, you get the 64. So the square root of 64 is 8, but the cubed root of 64 is 4, and you even could say the 6th root of 64 is 2. Not there, but just a quick little example. All right, so in the case of part C, you can see now we'll do the 5th root of 32. So what number times itself 5 times gives you 32? Just 2. And then part D right here illustrates the scenario where we have a numerator other than 1. So we can write this as the cubed root of 8, and then we can consider it as all squared. So this is one approach. If you do it this way, it's just simply going to be 2 squared, which is ultimately just 4. An alternative was the cubed root of 8 squared is the cubed root of 64, which is still 4. So either one of them work. That was just an example to illustrate the different scenarios. Any questions on A, B, C, or D? All right. And as mentioned a few moments ago, we really do want to have some powers in our mind. So I would recommend, and I'm going to maybe start us off, but you may want to just do this a couple times sometime before the test to say, okay, let's take some numbers. Let's say n is equal to 1, 2, 3. Let me zoom in here a little bit. 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. I don't know. I just kind of went up. I just chose like the first 13 numbers, no specific stopping point. What are the squares of all of those? So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared 16, 25, 36, 49, 64, 81, 100, 121, 144, 139, 169. And just to have some numbers in your mind as you go through chapter 4 that are perfect powers will be helpful. So I would also encourage you to just do for the cubes and do like 1, 8, 3 cubed is 27, 4 cubed 64, 5 cubes 125, and maybe even do like end of the fourth and do like 116, 81, and that's where I think 256 is the next one. So I just can't stop. 625. Okay, I'm done. Just can't stop once you get started. It's like so powerful. Get it? Powers. Okay. So just spending some time to have those numbers in your mind will pay some dividends as we go through this lesson. So that's a quick review of the exponent properties. Again, does anyone need me to clarify here? All right. Then let's go ahead and look at the actual definition of the logarithmic function and see how it relates to what we already know. So I did mention this earlier. The logarithmic function, it is the inverse of the exponential function. So it is the inverse of the exponential function. A couple things you want to call about inverses. First, domain and range switch. The other thing is that they cancel each other out. So we'll use both of those ideas, primarily the second one today. So for x greater than 0, so this is our domain. The domain of the logarithmic function is going to be just the positives. And the graph, we won't use it too much in this course, looks like this. Again, it's just reflected over the line x equal to y. I'm just going to state it here, but for really the rest of chapter 4, we won't really need the logarithm and the graph in this course. So that's okay. What we want to observe, though, is the relationship between the logarithm and the exponential. Both of them have a base. It's all about that base. I said that last time. So be careful as you write that base, though. One thing I want to call out is that as you write this, there's my writing line. That base is a subscript. So make sure that when you're doing your homework as you type it in, that you actually make sure you do a subscript if you have to type in a base. On the test, it won't be as big of a deal because the test this semester is multiple choice. So now, what observations do we want to make about this? The log is a function, so it has an input. The input to that function is x. If you were to look at the number closest to the base in the logarithmic form, it is actually the same number that is farthest from the base in the exponential form right there on the right. Same principle applies whenever you look at the logarithmic form of the number that is farthest from the base would now be the exponent when you're considering its exponential form. So this is best understood by just doing some examples. So let's zoom back out and maybe just fill this in. That is to say the function f of x equal to log base, and notice that I wrote that b as a subscript, so log base b of x is the logarithmic function with base b. One last comment on the form right here. There are basically some parentheses around the x that say, hey, that x is the input to the function. So we'll need to maybe think about that a little bit more in the next lesson, but for now, just realize that there's the log, there's the base, and then there's the input, and it's going to be equal to some number. All right, so let's do two examples right here below. This is the way you read this. So log base 3 of 9, so of 9 is equal to 2. So to write this is equivalent to saying, okay, the base, which is 3, raised to the 2, which is on the opposite side, is equal to 9. So those are equivalent statements. Try to notice the patterns as we go through this. If you look at log base 3, how does 9 relate to 3? Well, 9 is simply 3 squared. And notice that log base 3 of 9 is equal to 2. So here's something I think a lot of students miss as they initially learn about logs. This log base 3 of 9 is a number. And how you get that depends on the properties of exponents. So again, just to prove that, so you can see if I were to take a calculator, log base 3 of 9 is going to be equal to 2. Log base, let's say 4 of 64 is going to be equal to 3, kind of going back to our discussion that the cubed root of 64 is 3, things like that will show up. So try to pay attention to those patterns as we do switch between the two forms. All right, so let's go ahead and do the other direction. That is to say, I'm going to start with an exponential. And let me see if you all can remember this. What is the base of the exponent here? 4. So the base of the exponent will become the base of a log. You will go to the number that is farthest away from the base to get the number that goes next to the log. And then this will be equal to whatever the exponent was in the other form. Any questions there? Okay, let's do one more together, and then I'm going to pause to see if you all can handle a couple. All right. So first thing you want to do, identify the base. So if I looked at this, I want to say, okay, what is the base? The base is going to be 5. So my goal is to write this in an exponential form. So the base of the log becomes the base of the exponent, which I will go to the other side to get the exponent. So I got the 2. Then it will be equal to x. So yeah, you could simplify that, and maybe you'll even see like, oh look, 25 is what needed to go there for it to be equal to 2. But for now, all we're asked to do is write it into its exponential form, and that's what we did right here. So it's going to be base cubed is equal to 64. So if you think about the number that we cube to get 64 is 4. So b is 4. So just paying attention to those relationships as we go through will really be helpful to simplify these. All right, how many got just number 2, just so I can kind of see the majority of you? Very good. Let me go ahead and do a couple more, as it does illustrate a few more things we'll want to pay attention to. Number 3, the base is 3. I'll go to the other side to get y, and I will set it equal to 7. Number 4 and 5, well, 4, the base is 3. I go to the other side to get the 2, and I get equal to 9. And also notice that that is mathematically correct. And the last one, the base is 2. I go to the other side to get negative 3, and I set it equal to 1/8. Notice that the negative is equal to a negative because the input was a fraction. So that's going to be something that's worth holding on to as you get the hang of simplifying logarithms on the next page. Any questions on switching to its exponential form? In that case, we'll go ahead and do 6 through 10, where we are asked to write an equation in its logarithmic form. But a lot of the same thought processes apply. What is the base? The base here is, well, what do you all say? 12. So we have log. Its base is going to be 12. We go to the other side to go ahead and get whatever, in this case, it's just the symbol x, and then it's going to be equal to whatever the exponent is, which is 2. All right. Go ahead and try number 7. Let me give you 10, 15 seconds to see if you could synthesize the idea. All right. So log, the base of the exponent is 5. That becomes the base of the log. We go to the other side and we get the fraction 1 over 125. And then we set it equal to minus 3. So that is the logarithmic form. That's equivalent to the given exponential form. How'd you all do? How many got it? Good. Many of you got it. Any questions? All right. The other cases, or the other examples, illustrate a few other kind of corner cases. Remember that a radical could be rewritten as a power, so as a fractional power. So this is going to be 343 to the 1/3 is equal to 7. Just remembering that the index of the radical is the denominator of the fractional exponent. Now to rewrite it in its logarithmic form, I'll have log. The base of the exponent becomes the base of the log. Then 7 is the input to the log, and it will be equal to 1/3. One thing to pay attention to here, notice when the input is smaller than the base is when we're going to end up getting some sort of fraction. So the input, 7, is smaller than the base, so we do get a fraction. All right, so just hold on to that. That'll help you as we go. In the case of number 9, we end up with log base 4. of 2 is equal to 1/2. Again, notice that the base is larger than the input, or the input's smaller than the base. So again, we have the fraction. And then lastly, we have log base 2 of 32 is equal to 5. Any questions on these? Okay. So this is pretty nice because we could go ahead and just switch between the two forms. On the next page, you'll just be, let me cross that out, you'll just be given something like this. So one thing that I do want to kind of call out right here is, again, the relationship between the base and the number that is the input. What do you notice about 32? Can you write it as a power of 2? Hopefully you can see that 32 is just simply 2 to the 5th. So here is kind of where we're going. So this is our answer to this problem, but just to illustrate something, I can rewrite 32 as 2 to the 5th. And remember, the other thing I said earlier about was not just the domain and range switch, but that they're inverses, they cancel. So notice here that the base of the log matches the base of the exponent. So the answer is just simply whatever the exponent is. So when the base of the log matches the base of the exponent, they simply will cancel and the exponent is the answer. Let's explore that idea more on the next page. All right. Any questions there? Okay. Number 11. So we're not equal to anything here. We're just asked to evaluate it. So first of all, what is the base? The base is 2. So the base cannot change because, as we said, it's all about that base. You don't want to change it. So that stays the same. But can I rewrite 16 as 2 to some power? Is there some power I could put in that box that would give me back to the original? 4. I can rewrite 16 as 2 to the 4th. I have matching bases which cancel. So my answer here is just 4. And another way to go about this, I like the way I just showed it because it allows you to work with these inline. But another way you can do this is just say, okay, log base 2 of 16 is equal to some number. Let's just call that some number x. And then if you switch it, you get 2 to the x is equal to 16. But notice, again, is that same thought process. What power do you need to get the matching? So again, that answer would be 4, which would be the same there. So I really would emphasize do it that top way because that allows you to work with them inline. I think the homework actually explains it like the bottom for section 4.2, but 4.3 will need what's up above. All right, so let's go ahead and do a couple more together and see if the idea sticks. All right, so number 12. The base is 7, so I'm going to still need log base 7. So look at the number, 49. Is 49 a power of 7? It is, 7 squared. So I'm going to have 7 squared, but if I want the 7 to be in the numerator, I also need to remember to make it negative. So notice now I have matching bases. The base of the log matches the base of the exponent, so our answer here is negative 2. All right. Let me leave 11 and 12 up, and let me give you maybe about 15 to 20 seconds just to see if you can make any progress on 13 and 14. Sometimes just that moment to invest yourself in the problem puts a little bit of curiosity that kind of excites the answer. I don't know. Maybe that's just me. All right, let's go over 13 and 14 together. So this is something I was alluding to earlier. Notice that the base is 25 is larger than the actual input. So I need to go ahead and put a 25 here, but I need some number that when I raise it 25 to that some number, it gets me back to 5. Was anyone able to figure out that number? Well, if you think about it, I really need to take the square root. But how do you write the square root as an exponent? Using a fraction. So you would rewrite 5 as 25 to the 1/2, at which point you have matching bases, which cancel. So the answer here is 1/2. I'd recommend putting a star by that one. That's probably one of the most commonly missed questions on the test, the one involving the square root or radical. Okay. 14 is actually a little bit easier because you didn't have to mentally think about the radical. You just say, okay, log base 2. The 2 has to stay the same, but the fifth root could be rewritten as 2 to the 1/5 power. Bases match, so log base 2, and then the base of the exponent cancel, so the answer is just 1/5. All right. Any questions on 13 or 14? Okay, 15 and 16. Let's, of course, zoom in on 15 first. Anyone think they know the answer? If you do, just simply say it out loud. I'm hearing ones and zeros. And those are the answers to the last two. And the answer to 15 is going to be 1. Because remember, and when it's not written, it's understood to be raised to the 1 power. So the base already matches. So the answer here is just simply 1. 16, on the other hand, if you look at this, we have log base 5, and I want this to be a 5 here. And if I raise that 5 to the 0, it would put me back to 1. So the matching bases we now have cancel. So our answer here is simply 0. Yeah?
So the whole point of this is getting the numbers to match the base?
Yes. Because if you could get matching bases, the inverse property applies, which cancels them out. And then you get our answer. Yeah?
Why did you do 5 to the 0?
Say that one more time.
Why'd you put 5 to the 0 power if you're trying to match the base?
Sure. So the base of the log is 5. The log can't change. It's already cut down. You don't want to have to roll around logs. That's a bad tree joke. But the base of the log right here is 5. So I need this to be a 5, but it's given to be a 1. So I need to be able to get back to here. So if I do 5 to the 0, that will put a 1 back in my original problem.
Oh, so you just need to make that second number equal to the number at the top?
I need these two to match. Oh, but yes, what you said. I need this number to be equal to what's highlighted in red right there. Yes, that is correct. These take a little bit of practice. Let me go ahead and let me give you 2 minutes to practice these. So I'll go ahead and slide back up to this, but let me give you 2 minutes to go ahead and slide down to page 194 and try 37 through. That's okay. Let me go ahead and go over these briefly. We'll talk about the special logarithms, and if anyone still needs some more help, I'm happy to go ahead and help. All right, so I'm again just going to talk through these just at a comfortable pace. If anyone needs me to clarify something, do feel free to ask. So 37, the log has a base of 5. Therefore, I want a 5 here so I could cancel them. And what I need to do is raise it to a square, so because 5 squared is 25. Once I have that, matching bases cancel, so we're simply equal to 2. In the case of 38, Same principle, we just have to go the other way. So we have log base 8. I want an 8 here. And one thing that might be easier to think about this is not necessarily to think about how do you turn 8 into 2, but think about how do you turn 2 into 8. You cube it. So to go the other way, then you just take the cubed root or a 1/3 power. So our answer here is just 1/3. 39, log base 3. I want a 3 right here. And I know that 3 cubed is equal to 27, but because of the fraction, I'm going to have it be a negative, because the negative would send me back to that 3 cubed to the denominator. So our answer is -3. Any questions on those first 3? All right. In the case of 40, we have the square root. And again, if it's not specified, you would just assume that that's going to be a square or a 2. So rewriting this, this is log base 6, and then it's going to be 6 to the 1/2. Matching bases cancel, so the answer is just simply 1/2. Where do I get the 1/2? Sure. So the square root is this, whenever a number is not there, you assume it is 2. So that's where the 2 comes from. Now the 1, on the other hand, comes from the fact that this is 6 to the 1. So that's where I got that number right there. So maybe just to do one more example, just to see, to help you out. Let's do something where we have something other than 1. So let's say we have log base, someone give me their favorite number. 7. Log base 7, and we have, let's say, the 3rd root of 7 squared this time. So I'm adding a square here just to change it up. So this is just simply going to still be log base 7, and then I'm going to rewrite this as the cubed root of 7 squared as a fractional exponent. So it's going to be 7, but then the 2 goes in the numerator, a 3 goes in the denominator, so it's going to be 2/3. Does that help? Just sometimes seeing so it's something other than 1 helps. All right. The last 2 were very similar to the last 2 from earlier in the lesson. This is log base 5. I need a 5 next to the log, so that's going to be 5, and then to get back to 1, it's going to be 0, so our answer is 0. And again, just to maybe emphasize, the reason is because 5 to the 0 is equal to 1. And the last but not least, there's an understood 1 on there, so the answer is simply going to be 1. Does anyone need further clarification on any of these 6 exercises? Okay. Talking through 39 again, sure. Let me zoom back in. The base of the log is 3, so that I can't change the base, I'll leave that there. So what I want is a 3 right here so they could cancel. So I want to basically consider the relationship between 3 and 27. 3 cubed is 27, but that 27 is in the denominator. So to get it in the numerator, I would need to use a negative exponent. Does that help? Great. Any other questions? All right, then let's slide back and finish up the lesson, and we'll call it a day and go get ready for the storm, right? Okay, so back to the lesson. Well, there's 2 types of special logarithms. The first one I alluded to earlier when we talked about e, but like the number pi, which is approximately 3.14, Euler's number e is approximately 2.7. It goes on forever. It's like, again, you could always illustrate that by looking at a calculator. I typed it in earlier. If I simply just cleared everything there, did 1, it's 2.71828182885. Has a nice little pattern there at the beginning. Unfortunately, it doesn't repeat because it's irrational. But a logarithm with base e is called the natural logarithmic function. One thing I want to emphasize about this is that it's called the natural log. So the notation, this shows up a lot in the sciences. So instead of writing log base e, what we'll go ahead and write is ln of x. So if you see ln of x, that's the same thing as log base e. And let me emphasize this because I usually get an email from a student saying, hey, I keep missing this. That letter is an L, not an I. So when you type it on the keyboard, it looks like like a capital I, but that would cause you to miss your homework. So this is the letter L. So just emphasizing that that is an L, not an I. So make sure you type it correctly as you do your homework. The X right here is the input. So you could almost kind of imagine that the base is an E right there. So that's a notational thing that just because that function shows up a lot, it has its own symbol, which is ln, and the base is implied. Does that help? Yeah. Great. So we'll practice that down below. The other special logarithm is that with base 10. It's called the common logarithm because we work in a base 10 number system. We have 10 base digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's a decimal or a base 10 number system. So log, what we would use right here is we would just omit the base. So when the base is not written, you assume it's 10. So these are those two special cases. So all of the same properties below apply down below. For example, 17. It's not specified here, but we could assume because it's not specified that the base is 10. Let me zoom in here, makes it a little easier. So again, when you assume that base is 10, well, notice that you have matching bases, so they cancel, and the answer is simply 9. $18, there's a little bit more work to do first. Again, the base is going to be 10. So log base 10 of 1,000, well, 1,000 is simply 10 cubed. So because the bases match here, we could go ahead and cancel. And we are left with an answer of 3. So now that you've seen 2 examples, let me give you about 30 seconds to see if you could answer any of the ones down below. We'll still go over them, but just investing in the problem first. Let's see if anyone was able to get it. And then if anyone does have questions, I'm still happy to further clarify. Number 19, nothing too crazy here. It's just recalling that the base is 10 when it's not specified. So when the bases cancel, our answer will simply be equal to 4. In the case of 20, the base here is e. So if I were to rewrite this as ln of e to the 0, because 1 is the input, and then e to the 0 gets you back to a 1. Well, the bases cancel, so the answer here is 0. 21 is probably the easier one because, well, the base is e, and the base of the exponent is e, so those cancel, and the answer is simply 4. And then last but not least, number 22, the fraction, well, if you want to write this in 2 steps, I can rewrite that fraction as e to the negative 6. And then the bases cancel, so our answer here is just simply negative 6. To illustrate, there's assumed to be a base e, which cancels with the base of the exponent, and then you end up with negative 6. So So that's a quick look at logarithmic functions and how to evaluate them. We'll look more at their properties next time. Anyone have any questions? If you do, stick around. I'm happy to help. Otherwise, be safe, and I will see you all on Friday.